You've written this 100 times. Y equals c₁cos x plus c₂sin x, the general solution to y double prime plus y equals 0. Two constants, two functions. There's a reason it's exactly 2, not 3, not 1. And there's a reason it looks like a linear combination. It is 1. And this is a linear algebra problem in disguise. The answer comes down to one word: dimension. Start with y double prime plus y equals 0. Suppose y1 and y2 are solutions. Form c1y1 plus c2y2 and substitute. Linearity of differentiation gives c1 times the quantity, y1 double prime plus y1, plus c2 times the quantity, y2 double prime plus y2. Both quantities are 0. y1 and y2 are solutions. So c1 times 0 plus c2 times 0 equals 0. Any linear combination of solutions is a solution. That's closure under addition and scalar multiplication, the defining property of a vector space. The zero function is also a solution, the zero vector. These vectors are functions, not number columns, but the axioms hold. This closure property reveals an operator at work. Define L of y as y double prime plus y. L is a linear operator. L of c1y1 plus c2y2 equals c1 times L of y1 plus c2 times L of y2. Now the equation becomes simply L of y equals 0. The solution set is every function that L maps to 0. In linear algebra, that set is called the null space, the collection of all inputs and operators sends to 0. Let's compare. On the left, consider a matrix A acting on a column vector x. The null space of A is the set of all x such that A times x equals the 0 vector. On the right, our operator L, which equals d squared over dx squared plus 1, acts on a function y of x and sends it to the 0 function. The null space of L is the set of all y such that L of y equals 0. A dashed line connects both panels because they share the same structure. The solution space of our ODE is the null space of L. The same concept as the null space of a matrix, but now applied to functions instead of vectors. The solutions to our equation form a null space. Here's the key theorem. For an nth order homogeneous linear ODE, the solution space has dimension n. Recall that a basis is a linearly independent set that spans the space, and the dimension is the number of elements in any basis. Our equation y double prime plus y equals 0 is second order, so n equals 2. That means the dimension is 2, and we need exactly 2 linearly independent solutions to form a basis. Let's verify that cosine x and sin x both solve the equation. First, the second derivative of cosine x is negative cosine x. So cosine x double prime plus cosine x equals negative cosine x plus cosine x, which equals 0. Check. Next, the second derivative of sin x is negative sin x. So sin x double prime plus sin x equals negative sin x plus sin x, which equals 0. Check. Now we need to confirm they are linearly independent. Neither is a scalar multiple of the other. We use the Wronskian. The Wronskian is the determinant of the matrix with cosine x and sin x in the first row, and negative sin x and cosine x in the second row. This gives cosine squared x plus sin squared x, which equals 1. Since this is not 0, the Wronskian confirms linear independence. Therefore, the set containing cosine x and sin x is a basis for the solution space. The general solution is y equals c1 times cosine x plus c2 times sin x. This is a basis expansion where c1 and c2 serve as coordinates in this basis. That basis isn't unique. Consider R2. The standard basis vectors, 1, 0, and 0, 1, describe every point in the plane. For example, the point V equals 3. 1 can be written as 3 times E, 1 plus 1 times E2. That's 3 times 1, 0 plus 1 times 0, 1, which gives 3, 1. But now consider a different pair of vectors, 1, 1, and 1, negative 1. These also form a basis for R2. The same point V equals 3. 1 can be written as 2 times 1, 1 plus 1 times 1, negative 1. Let's check. 2 times 1, 1 gives 2, 2, and 1 times 1, -1 gives 1, -1. Adding those together, 2 plus 1 is 3, and 2 minus 1 is 1, so we get 3, 1. Same vector, different coordinates, 2 bases, 1 vector, 2 descriptions. And this principle extends to function spaces as well. Cosine x and sin x are one basis for our solution space, but a single space can have many different bases, and each one gives a valid coordinate system. Consider e to the ix and e to the negative ix. Take e to the ix, its second derivative is I squared times e to the ix, which equals negative e to the ix. Add e to the ix, negative e to the ix plus e to the ix equals 0. It's a solution. The same calculation works for e to the negative ix. These two functions are linearly independent, so they form a second basis for the same two-dimensional space. The link between these two bases is Euler's formula. Cosine x equals 1/2 e to the ix plus 1/2 e to the negative ix. Sin x equals 1/2 I times e to the ix minus 1/2 I times e to the negative ix. These are change of basis equations, expressing one set of basis vectors in terms of another. The coefficients form a transition matrix. Euler's formula is a change of basis matrix for a function space. One more powerful connection. When we specify initial conditions, y of 0 equals a and y prime of 0 equals b, we uniquely determine c1 and c2. Let's see how. Substituting x equals 0 into our general solution, y equals c1 cosine x plus c2 sin x, we get c1 times cosine of 0 plus c2 times sine of 0. Cosine of 0 is 1 and sine of 0 is 0, so this simplifies to just c1 equals a. Now for the derivative, y prime equals negative c1 sin x plus c2 cosine x. Substituting x equals 0 gives negative c1 times sine of 0 plus c2 times cosine of 0, which simplifies to c2 equals b. So initial conditions fix the coordinates in the basis. This is exactly like choosing a specific vector by fixing its coordinates. Now step back and see the big picture. A course in linear differential equations is really a course in finding bases for function spaces. The general solution is always a basis expansion, and the number of arbitrary constants equals the dimension of the solution space. This pattern holds everywhere. Consider y prime plus y equals 0. This is first order, so its solution space is one-dimensional, spanned by e to the negative x. The equation y double prime plus y equals 0 is second order, giving a two-dimensional space with basis cosine x and sine x, and y triple prime minus y prime equals 0 is third order, yielding a three-dimensional space with basis 1, e to the x, and e to the negative x. In every case, the order of the equation equals the dimension of the solution space. Eigenvalues, eigenvectors, tools born in linear algebra, become the primary machinery for solving differential equations. Next time you write a general solution, see a vector space and the basis you chose to describe it. Every general solution is a basis expansion.